Okay, what's the Swedish country called?
Sweden.
That's the one, thank you. And zwei, Polizei. Drinking and thinking, occasionally tinkling, let's talk some science.
Oh yeah, that's the stuff. You okay there?
Oh, God, it's so bad.
As we keep reiterating, David hates whiskey and all its other forms.
I'm not about that life.
Welcome. I'm Eric Dwong, the author of thephysicsbehind.com.
And I'm David Rutz, a mechanical engineer.
Yeah, we're here at Crafty Pint here in Dublin, I guess I would say. And this is
Still
Gin
in
and
Dublin.
Jargon. Yeah, this
Welcome.
is Gin and... Yeah. This is Gin and Jargon, our podcast about science in general.
Yeah.
Physics mostly, but science, yeah.
Yeah.
What we just took was the Basil Hayden. It's a bourbon. And it's very much a bourbon.
Unfortunately, it was.
I thought it was delicious.
You know, either way, whether it was more whiskey or more bourbon, it was bad for me.
Nah. What do you got there?
I have got the, the Mad Tree, what is this? Vernal Beckoning.
I told you to write it down.
I did. It's written down over here for me. I can either look at the table or I can
what's vernal beckoning?
Oh, it's a Belgian ale.
Belgian ale, okay.
It's okay.
Oh, not a fan?
It's okay.
Huh.
I'm not saying it's bad. I'm saying it's
Every
okay.
drink you've ordered so far has been in a snifter. It's all about that, I guess.
They apparently think I'm a classier gent than thee.
Well, mine keep coming in pint glasses. This is a Homestead Galactic Heroes IPA. It's from Ohio. I don't know where in Ohio. Didn't bother looking, but it's from Ohio.
We could do a podcast there.
Yeah, we should record at more local breweries.
Mm-hmm. They've got weird hours, though. I think that's the problem.
So do I. It's all good.
So yeah, welcome to the podcast where inebriation and discovery go hand in hand.
Indeed. So we have two goals right now, and it's learn something and also get drunk.
Those are the ones.
Yeah. So let's start off with some news items, yeah?
Let's do some news.
All right.
So China is getting into a market I didn't expect. They're looking for alien life.
Or that's rather the way that the news article would spin it to get you to read it.
Okay, fine.
Right.
They're building, the largest radio telescope.
The largest radio telescope in the world.
Which is pretty darn cool no matter how you spin it. Right?
Exactly.
What do you find with radio telescopes? You find radio signals. Where do you get radio signals from? Mostly dying stars, black holes, that sort of thing. But also potentially
and also
alien
all kinds
life.
of background radiation in the universe. It's all over the place. Well, it depends on what bands they're looking at, but in general, radio telescopes will pick up all kinds of stuff.
Absolutely.
But they spin it in that way to make it more interesting for other people to read because a source of radio signals would be. We put out tons of radio signals.
We're brimming with them.
Yeah, and any other any other alien life would presumably put out radio signals that we could hear, potentially.
If they're, technologically advanced enough.
Right.
So, our first signal to the universe was, I believe, one of Hitler's speeches.
Really?
Yeah. Did you ever see the movie Contact?
No.
So that was the premise of the movie Contact. We've been searching the sky with SETI, that program to search for extraterrestrial life. And
that's the acronym. Search for extraterrestrial life, yeah.
Well, what's the...
Intelligence.
Intelligence, that's the one.
Yeah. So side note, did you know that you can network your own computer into SETI's...
What?
Yeah, look for it. It's like a screensaver.
Man.
Like when you're not using your computer and it goes to a screensaver, you can devote your computing power, what little you have, whatever.
Right.
You can devote your computing power to help with SETI.
I am so doing that.
Yeah, look it up.
It's
cool. Dom used to do it.
So in Contact, which is a book written by Carl Sagan.
Oh, okay.
They made a movie of it, and the premise is our first signal was our first broadcast signal was the speech that Hitler gave in Nazi Germany. He was a great speechwriter. The content's a little morally questionable, but we received that signal back from somewhere in space, but its signal is strengthened, so we know that something has intentionally sent it back. It's undercoded with a bunch of like instructions to build this machine to go join the aliens. And it's not like
Jodie Foster in it.
Yes, it is.
Okay,
She's the star of that one.
Yeah.
And it's the book and the movie are both very spiritual at the end, saying that this is a journey. We're still looking for this, but the idea is still pretty cool. We've been sending out radio signals now for coming on almost 100 years.
Mm-hmm, yeah,
and
which is like a blip in the grand scheme of things.
It's an itty bitty blip. And that's a whole nother topic that I'd love to get into sometime. I think it's the Fermi paradox. That why don't we see more life out there? Mm-hmm. But that's something else.
Yeah.
Suffice to say, it'd be cool if we found life, but most likely we're gonna find some quasars.
Lots and lots of quasars.
That was one thing that's going on. Is China's in their new telescope,
and they've been actually making a lot of headway into space in general. They've got a lot of plans for, I couldn't tell you in detail, but a lot of plans for... they have a lot of plans for like other space things, a lot of experiments and flights, and in general, they've really surged forward in a lot of ways. Some people would find it threatening, I suppose. I kind of find, any advance into science is a good thing, really, because the scientific community is a lot more diplomatic than the political community really is. That's why there's astronauts in what are they called? Russian space. Oh God, what do they call them?
Kartoshka. I'm pretty sure that's potato.
Oh my God. Hold on. No, Russian astronauts. Cosmonauts. Yes.
Oh, that's what you were looking for.
Yeah.
I gotcha.
Yeah. Astronauts and cosmonauts working together on the ISS. Like they have no mind for what's going on down below.
Yeah.
There's no politics up there. They're all working together for science. That's great. I think Chinese astronauts are called taikonauts. So it's interesting that every country has its own name for it.
I wonder what Japanese astronauts are called.
I don't know.
Because
taiko is a Japanese thing.
It's a drumming thing.
Yeah.
Interesting.
Chinese.
But speaking of science's ability to be a lot more diplomatic than governments, science does this thing where if a theory is determined to be wrong, even a commonly held theory for decades or millennia, this commonly held theory is overturned. If it's wrong, it's wrong. You let bygones be bygones, let old theories that don't work pass away. And you know what? People who prove these things get Nobel Prizes.
Indeed. And this year, pretty big one came up.
Yeah.
In comparison to some of the more recent Nobel Prizes, the 2015 Nobel Prize went to two groups of people. Well, two people, but two people and their two people and their respective research labs. A Japanese man named Takaki Kajita.
Mm-hmm. Yeah, that's how I read it.
And a Canadian,
Arthur B. McDonald,
which is like
he does not have a farm.
Which is like the most generic name I could possibly think of.
Arthur B. When I first read it, I saw the B, and I'm like, why doesn't Takaki Kajita get a middle name? Arthur B. McDonald? Did
because he doesn't have
someone?
Did he assassinate someone?
Why are we referring to him with his middle name? It's just weird.
But they received the 2015 Nobel Prize for their work in particle physics.
Yeah.
In comparison, and I don't mean to lessen a Nobel Prize winner, but there's some Nobel Prizes that are just awarded to people that have really big breakthrough things, and some Nobel Prizes that just seem a little less,
monumental.
Yeah. Not to say that their accomplishment is not monumental, it just doesn't seem as big of a breakthrough in the science community. So the 2014 prize was awarded to two guys for the invention of the blue LED, which...
What?
Yeah.
Wait, why is... Okay, explain this to me. I'm intrigued.
So the blue LED, I mean, is a revolution in lighting technology because it allows you to create white light with an LED. Previously, you could only create like red and green, I think. So when they invented the blue LED, that like it revolutionized. You can make white light, which is important because like LEDs consume like orders of magnitude less power than other forms of lighting, and they last a lot longer. So you can thank them for essentially most of lighting in the modern world. Anything that uses an LED that has a blue LED in it, which is most LED things these days, can be attributed to them. Like, it's a huge breakthrough in technology, but not in like pushing the boundaries of science,
Yeah, it's something that I guess was doable, but we just needed the right combination of intelligent minds to be able to do it.
Yeah. But yeah, this new one is a huge push for physics.
And this isn't a tech thing. This is more of they've discovered something that completely turns physics on its head.
Yeah, exactly.
For the past 80 years, we've been operating under the assumption that neutrinos are massless, and now we have other evidence against that.
Yeah. So
if some of that didn't make sense, don't worry. We're getting to it.
We're getting to it. So they received their prize for a concept that they call neutrino oscillation.
That's a neutrino wobbling.
So where do you want to start with this? You want to start with what are neutrinos?
We should probably start with what are neutrinos, right?
Yeah.
Neutrinos are wobbly. Who cares? Neutrinos change from one form to another.
Wobbly.
Who cares? What the hell is a
Doctor
neutrino?
Who shit right there.
A wibbly wobbly tiny whiny.
Oh god, don't get me started.
Neutrinos are just that, traveling near the speed of light.
No.
Anyway, yeah. So
it all started with something called beta decay.
Yeah.
So beta decay is a type of radioactive decay where like some atom breaks down into a different type of particle, and on its way there, it releases an electron. It releases an electron. When they first experimented with this, when they first saw this happening, they were a little puzzled because the amount of energy that the particle should have started with and the amount that the electron had didn't line up.
Yeah, it's like they gave a dog a gallon of water and it only pissed out half a gallon. What's with that?
Right, where's the other half gallon? Yeah, that's exactly the problem that they had. So, people kind of thought about it. They're like, there must be something else there that it's giving off with some energy. And a man named Wolfgang Pauli, who's more famous for his other ideas, I suppose, came up with the idea that there was another particle there that was massless, but that carried that energy away in some other way. He called it a neutron. Actually, he called it a neutron.
He called it a neutron. Yeah.
It was Fermi, another scientist, who called it the neutrino.
I believe he called it a poltergeist because he wasn't speaking our language here. He said it was a little ghost, right? That was just running around. Where did you go, little ghost? Because not only is this
his name
particle
is Wolfgang.
Yeah, Wolfgang. It was referred to as poltergeist.
Oh, okay.
But not only is this particle massless, so gravity doesn't affect it, but it's neutrally charged, so it doesn't have any magnetic charge on it. You can't influence it with a magnet.
Electric charge,
electromagnetism.
Right.
So this is kind of an elusive thing. How do you detect it? And that's exactly the problem that Pauli had with this. Is he's like, I've committed a grave error in the science community. I've theorized something that is impossible to disprove.
Right. What? And it's hard to detect because it's chargeless. And that was a problem for a long time. Yeah. But they eventually figured it out.
They did.
And what they did figure out is that there has to be another particle there that's taking away that energy. And so a scientist named Fermi, he dubbed it the neutrino. It's like, I think, an Italian term for neutron.
Yep, that's exactly it.
Yeah, so we call it the neutrino. And neutrinos are these little, thought to be massless particles that carry away some of that energy. They're just a byproduct of the beta decay.
Yeah.
And over time, they discovered that not only do electrons have a neutrino counterpart, but other particles do too.
And so just all these different decays produce all these different neutrinos, right? So you've got
Right.
these different neutrinos arising from different decays.
Right, and so
you know,
to date we have 3 so far.
we have 3.
Yeah,
And, the funny thing about neutrinos, they're the second most numerous, second most prolific particle in the universe.
yeah.
Second only to protons. And
Yeah.
the light. If you're familiar with light, Photons, I'm sorry. Yeah, photons. If you're familiar with light, photons, that's what they are.
They're everywhere.
So neutrinos, like billions of them, are passing through your body every second.
Yeah.
Now, don't be scared. We said that was radioactive decay creating them, but it's like everything decays. If you ate a banana today, you're having potassium atoms inside your body right now that are decaying, and they're creating about 500,000 neutrinos that are going to blip through your body. So this isn't a harmful radiation.
What's the half-life of potassium?
Oh, I don't know.
What do they beta decay?
Apparently.
Oh, really?
Yeah.
I don't know. The half-life of bananas.
Yep.
Because if I say no, the half-life bananas is until they turn brown.
Yeah, exactly.
But yeah. So to date, there are 3 known neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino.
Yeah.
So they're like 3 different types, or we call them flavors.
I don't think they're flavors. I think they're just
Flavors
types.
are it.
Flavors.
Flavors is another thing, but we love flavors. The physics community loves flavors. But anyway, yeah. So
there are these 3 different types, and the problem was up until this year, up until this discovery, was the sun, which is causing nuclear reactions in its core constantly, should be emitting a certain number of electron neutrinos.
And we have a pretty good idea. We have a very, very good model of how many that should be.
And because we can see how much energy the sun is producing, we know the processes that are going on inside the sun.
Yeah.
But you know how many neutrinos we measure when we measure for those electron neutrinos? About a third. About 1/3 of what we should be.
Right.
Yeah.
And so there was a Japanese lab. Well, people have been noticing this for a while.
Yeah. No, this is a problem that's been known for a while.
Yeah, kind of plaguing the physics community for a while. That the detection of these electron neutrinos is not as high as it should be. Now they thought about a couple of things, like maybe it's a problem with our equipment, maybe our model of the sun is wrong. So a lab in Japan and a lab in Canada, or as I like to call it, Canada, came together. Well, not came together. They kind of found this independently.
They compared notes.
Yeah, basically, if you want to get down to it, basically what happened was they each figured out in some way that the amount of electron neutrinos they were detecting in their equipment was not as high as it should have been. In the Canadians' case, they were able to detect all 3 types of neutrinos. So they counted however many electron neutrinos they could get, and then they counted all 3 together. So what's interesting is when they counted just the electron neutrinos by itself, they found that there was a deficiency. They weren't getting as many electron neutrinos as they thought they were supposed to get.
And like we said, that's something that people have known for a while.
Right.
Like, so this was what they expected. And then they went on to measure
All 3 of them.
all 3 of them.
And the total number together is what should have...
It matched the data for how much energy should have been coming from the sun.
And atmospheric neutrinos.
And accounting for all the...
Yeah. So when they detected all 3, they were like, wait, the total number adds up, but we still get a weirdly low number of electron neutrinos. So this has led to the idea that, or I guess it's almost proof, that neutrinos evolve over time. They can change.
They just wibble wobble from one state to another.
Yeah, so they can change. They can change from being electron neutrinos to either muon or tau neutrinos. So, what's important to note here is that because they're changing, that makes them not massless. So, how do we know that? So,
I mean, I don't think we need to get into how we know that they're not massless, but that's the important end result here.
It's a short explanation, I think.
The particle physics model that we've got right now says neutrinos are massless.
Yeah.
And then makes a bunch of assumptions off of that.
Right.
That work in certain scenarios. But now we have concrete evidence that these particles are not massless.
Right.
We need a whole revision on the standard particle theory of physics. And there have been other indicators that the standard particle theory isn't quite up to snuff.
Right.
But they've been elusive and unproven up till now.
Yeah.
Which is why this discovery is so big and warranting a Nobel Prize.
Right.
This will turn particle physics on its head.
Right. So how do we know that these things are massless? How do we know that these things are massless? Because they change. So, in order for something to change, like, change requires that it was something before some time and then something else after some time, which means that this particle must experience time. Now, if it were massless, it wouldn't. And it comes down to special relativity, actually. If something is massless, like a photon, if something is massless, then it has to travel at the speed of light. And things that travel at the speed of light don't experience time. It's just one of those things about special relativity. I mean, you can do the math, but things that are...
It has to do with also, approaching the speed of light, time slows down until it's not observable.
Until you reach the speed of light, and then it's not observable.
And the only
Time
things that
stops.
can reach the speed of light are massless.
Exactly. So if a particle is experiencing change, then we know that it's experiencing time. And if it's experiencing time, then it can't be massless. So if we've determined that these neutrinos are changing, then we know that they're not massless, which is contrary to the previous belief that they are massless. Now, this discovery actually didn't come about this year. It was actually, published and well-known in 2002 or 2003. It's just that they, my explanation
They take a while.
the Nobel Committee is a committee, and so it takes a while for those things to come about. So we're just hearing about it now. We're just getting the Nobel Prize for it now, but it's been known for a while.
The gravitas has just taken effect.
Yeah. Well, we're back, and it's time for trivia. You went first last time.
Did I? Okay, then you're up.
Okay, all right. So, in the nomenclature for subatomic particles, a lot of them are, they have what are called flavors, right? So, quarks have a lot of flavors. A lot of particles have a lot of what are called flavors. My question for you is, what flavor is red velvet cake?
What?
What flavor is red velvet cake?
Oh, you were working. Okay, that's not what I was expecting.
Yeah.
Red velvet.
You've had red velvet.
I've had red velvet cake.
Yeah.
I don't
You've
really
never thought about what flavor it was,
No,
right?
I don't really like cake, and all cake sort of just tastes sugary to me.
Okay. Well, red velvet is very sugary, but it does have a flavor.
It does have a distinct flavor. Red velvet. I'm gonna say nutmeg.
You think it's nutmeg?
Let's go nutmeg.
Okay. Red velvet cake is actually just a really, really, really red chocolate cake.
Wow. Okay.
Yep.
All right. Way to go, red velvet. I guess.
It's just chocolate cake.
I do like chocolate.
Yeah.
Okay.
I mean, they use food coloring now, but they used to use
How did they get it
They used to make it They used to use beets to make it red. Yeah. But it's still, in essence, it's a chocolate cake.
That's funny. And they just add red hue to make it look different.
Really red, yeah.
That's funny. Okay.
That's you.
I know, that's me. I'm going to wait until you have to take it with me.
All right.
Boom. So, I'm going to ask you, we've been talking about neutrons, neutrinos, and you know that neutrino is Italian. What is Italian for? What does neutrino mean in Italian?
I think it is Italian for nothing. The word nothing.
Incorrect.
Damn.
It is Italian for little neutral one. There's this cute little neutral particle going around, and that's what it means in Italian. Little neutral one, just kind of cute as...
You got me.
I like it.
Well, cheers.
So this is... Oh, man.
Oh, these are
These are puckering Putins, and...
no doubt. a recent name given to this drink, I suppose.
A recent name given to this drink by one of my friends.
Oh, he made this up?
Yeah, we were camping and we had lime juice or lemon juice, and we had vodka, and we were like, well, what shots can we make with this? Lemon juice and vodka.
All right, well,
and, call it puckering Putin.
And now we're here. Cheers. Oh, damn.
You still got a bit in there.
Yeah.
Man.
I noticed that tragically too late. That is not an easy one to take. Well done. Okay, so and now that we're done with that, we want to talk a little bit about Nobel Prizes in general. Where they come from.
So Nobel Prizes just aren't awarded to homebodies discovering new things. They're awarded to people who put in the time and effort to make something that's or to discover something that's truly monumental towards science.
Yeah, and actually, it's kind of funny how it started. The Nobel Prize was first started by a man named Alfred Nobel, who is, I guess, most known for starting the Nobel Prize. Funnily enough, less known for being the inventor of TNT.
Is that what he invented? I saw that he was an inventor, but I didn't see.
He invented TNT, and he got really rich off of it because people were killing each other with TNT all the damn time. So
to give it due credit, TNT was extremely useful in the building of railways through mountains.
But also for blowing people up. Triglyceride, yep. And so he invented this stuff, and it made him a lot of money. And later in life, he kind of felt bad about it. And he decided that he would put his money towards helping humanity instead of killing it. And so he created like a fund with his own money to create the Nobel Prizes. This happened in 1895. And so the Nobel Prizes are awarded in 5 categories nowadays.
Chemistry, literature, peace, physics, and physiology or medicine, stuff to do with the body.
Yeah.
Though there is a 6th, the Nobel Memorial Prize in Economic Sciences, but that was sort of established by Sweden's central bank.
Yeah, that's separate.
Until,
that's separate than
1968, so that's a ways beyond.
So the Nobel Prize is awarded by the Royal Swedish Academy of Sciences, and they have a committee that chooses the winner for each year, and each winner gets a shiny gold medal. They get a diploma, and they also get $1.2 million US. Well, I mean, in the equivalent of $1.2 million as prize money.
Why 1.2?
I think it's like a rounder number in whatever weird Swedish currency.
8 million SEK.
SEK. Yeah, that's what it is.
What the hell is a SEK?
I don't. Just
okay.
Tell
us what a SEK is. You know,
I'm guessing
tweet
it's
us, whatever you want to do. Facebook, Instagram, email us on our website. Tell us what a SEK is, and you can suggest the next shot.
I would go so far as to guess that it's the Swedish currency. Guess they didn't join the euro, you know. So there's been a lot of Nobel Prizes awarded. They awarded the first one in 1901.
Yes.
The very, very first one went to the man that discovered X-rays. His name was Wilhelm Röntgen. And,
well done on that pronunciation. Well
thank
done.
you. You like the Wilhelm on that?
The Wilhelm Röntgen. And you even got the
Röntgen
in there.
Yeah. So he discovered X-rays. And ever since then, they've given one out for almost every year. There's a couple of years where they've skipped it. But almost every year they've given one out. And most of them have, most like notable scientists have received a Nobel Prize. At least most modern scientists have.
Most modern scientists have received the Nobel Prize?
Yeah. Albert Einstein received one.
He's not modern at all.
That's modern physics, though.
He's dead.
It's modern physics.
I feel like Modern should be things that people. I don't know. Oh, this is a different discussion. Continue.
I mean, but then there's a difference between like classical physics and modern physics.
Yeah.
So most of the people that are like pioneers in modern physics have received the Nobel Prize.
So if you've heard a name, they've probably received it.
Yeah.
Yeah.
I mean, for instance, Planck, Michelson, van der Waals, Hertz, Millikan, Einstein, Heisenberg, de Broglie. They all got Fermi, Pauli. They all got Nobel Prizes for their work. Madame Curie got one too for her work in radioactive substances. So
was she the first woman to get it?
I think she was the first woman to receive one, and she actually received a like a half prize because you can like 3 people at any one time can receive one Nobel Prize.
Okay,
and they usually share them between themselves. So in her case, it was 3 people, but one person received one, and then her and another person received half of one.
Gotcha.
Really weird. Yeah. So yeah, like most of the biggest breakthroughs in science have been rewarded with Nobel Prizes. Now, obviously, like they haven't awarded them to people that made like classical discoveries in physics. Like Isaac Newton doesn't have a Nobel Prize because he wasn't around when they were a thing.
That was several hundred years too early.
Yeah, exactly.
There was one more Nobel laureate related to neutrino. Let's see, Frederick Rines, who worked with Clyde Cohen in 1956. That they actually detected neutrinos on their detectors. And, of course, as soon as they did, they sent the results to Pauli, said, hey, you were kind of right. Look at this stuff.
Yeah.
But I don't think Frederick Rines got the Nobel for that, because he got it in 1995.
Oh.
So I'm guessing that was for something else. Because while the Nobel Committee takes a while, they don't take 50 years, or 40 years as it were.
Well, actually, like, if you were to ask a bunch of people, what did Einstein get his Nobel Prize in? A lot of people would say, like, oh, I don't know, E equals MC squared. He didn't get it in that, actually. Einstein won his Nobel Prize for the photoelectric effect.
Photovoltaics.
And, which was... I mean, like, I wouldn't say it was more important than E equals MC squared, because that's a really, really important sort of revelation, but the photoelectric effect is one of the first pieces of evidence for quantum mechanics.
Yeah.
That photons exhibit like a particle and a wave, sort of nature.
Their interaction on the quantum level was not really known before that point.
Yeah, so that idea of that photoelectric idea is definitely a pioneer into the field of quantum mechanics. You want to call it that?
Let's call it there.
All right, let's call it there. Well, thanks for listening. I'm Eric Dwong. This is David Rutz.
Howdy.
This has been Gin and Jargon. If you like what you hear, check us out on YouTube and on iTunes. We're also on social media, on Twitter and Facebook and Instagram now. So if you like photos, that's where we'll be. If you want to suggest a shot for either the beginning of the show or for the trivia section, type it in on Twitter and send it over to us, and we'll take your consideration to an account. There's no shot that is too hard, I suppose, for us. Yeah. But
we'll venture to the farthest reaches of inebriation at least once. Yeah. Special shout out for Casey Payne for mixing our episodes, and for Jack Dorn for working on our music. Toodly-too.
And see you guys next time, I guess.
Cheers.
Cheers.